So in this presentation, we have to talk about Dirac matrices. For that, consider the Dirac Hamiltonian of a free particle H equal to E equal to C alpha dot P plus beta MC square. In this equation, replace E by the energy operator and P by the momentum operator minus IH cross delta. We can get the equation of this form. Now allow these operators to operate on the wave function psi. We can get this equation. Here alpha dot del is obtained as alpha x dou by dou x plus alpha y dou by dou y plus alpha z dou by dou z. If we substitute all these values, we can get the Dirac's equation of form 1. From equation 1, it is clear that alpha x, alpha y, alpha z and beta are not numbers but are matrices. These matrices obey this rule: alpha x square is equal to alpha y square is equal to alpha z square equal to beta square is equal to 1. The eigenvalues of all the four matrices are plus 1 and minus 1 since their squares are unity. Furthermore, these matrices are anti-commuting in nature. See here, alpha x beta is equal to minus beta alpha x, alpha y beta equal to minus beta alpha y, alpha z beta equal to minus beta alpha z. So this equation alpha x beta equal to minus beta alpha x is modified as alpha x beta plus beta alpha x equal to 0. In the same way, we may write these two relations. First of all, we should know the meaning of commuting and anti-commuting nature of operators. If A and B are two commuting operators, then AB equal to BA. If A and B are anti-commuting, then AB equal to minus BA. So we may conclude that alphas and beta are subjected for anti-commuting property. Now take this relation: alpha x beta is equal to minus beta alpha x. Then pre-multiply this relation alpha x beta equal to minus beta alpha x by beta. Then this equation is modified as beta alpha x beta, which is equal to minus beta square alpha x. We know that beta square is equal to unity. So beta alpha x beta is equal to minus alpha x. Now we have to take trace on both sides. First of all, we should know the meaning of the term trace. Say a matrix is given to you. This is unitary matrix I equal to 1 0 0 0 1 0 0 0 1. If you make the trace of this matrix is equal to 3, if you take the sum of the diagonal elements, that is called trace. Trace of this I is equal to sum of the diagonal elements. So 1 plus 1 plus 1, that is equal to 3. So in this way, we can understand trace, so that we have to take trace on both sides of equation 5. Trace of beta alpha x beta, which is equal to minus trace of alpha x. One cyclic rule is present in matrix, that is trace of ABC is equal to trace of BCA, which is equal to trace of CAB. Now we should apply this rule: trace of ABC equal to trace of BCA for the left hand side of equation 6. Say trace of beta alpha x beta is equal to trace of alpha x beta beta, because this is A, this is B, this is C. Trace of ABC equal to trace of BCA. So trace of beta alpha x beta equal to trace of alpha x beta beta, which is equal to trace of beta square. Trace of alpha x beta square is equal to trace of alpha x, because beta square is equal to 1. So instead of trace of beta alpha x beta, we can write trace of alpha x. So this equation 6 is modified as trace of alpha x equal to minus trace alpha x. So trace of alpha x plus trace of alpha x equal to 0. 2 times trace of alpha x equal to 0. Then trace of alpha x equal to 0. The same condition is true for all other cases, that is trace of alpha y equal to trace of alpha z equal to trace of beta equal to 0. Then trace of alpha x equal to 0 is possible only when the number of plus 1 eigenvalues is equal in number to the minus 1 eigenvalues. This condition restricts the dimension of alpha x to an even number. Dimension means number of rows into number of columns. The smallest even dimension is 2 by 2. Already we have three anti-commuting 2 by 2 matrices called Polyspin matrices. They are sigma x, sigma y and sigma z. The value of sigma x equal to 0, 1, 1, 0. The value of sigma y equal to 0, minus I 0. Sigma z is equal to 1, 0, 0, minus 1. These matrices are called Polyspin matrices. These matrices are subjected to anti-commuting property. They are Hermitian in nature. Their squares are unity, so that they may have the eigenvalues of plus 1 and minus 1. If you want to clarify the meaning of the term Hermitian, just consider the matrix sigma y. If sigma y is Hermitian, it should obey the condition sigma y dagger is equal to sigma y. Here sigma y dagger means sigma y star transpose. Say sigma y is taken, the value of sigma y equal to 0, minus I 0. Sigma y star is equal to, just to change the sign of minus I into plus I, this plus I into minus I. 0 I minus I 0. Then sigma y star transpose, which means that this column is written as first row and the second column is written as second row. If you do that operation, we can get 0 minus I 0, that is our sigma y. So the condition sigma y dagger equal to sigma y is satisfied. Hence we can call this sigma y as a Hermitian matrix. The eigenvalues of sigmas are plus or minus 1 since their squares are unity. Already we discussed the point. It can be shown that a fourth matrix that anti-commutes with those three cannot be found. The next possible even dimension is 4 by 4. We cannot use these matrices for alpha x, alpha y and alpha z directly, because here we are operating with 4 operators, alpha x, alpha y, alpha z and beta. But a fourth matrix is not available to anti-commute with these three matrices, so that we have to go for the next higher order even dimension, that is our 4 by 4. Arbitrarily, beta matrix is taken to be diagonal with 2 plus 1 eigenvalues and 2 minus 1 eigenvalues. In this way, we have constructed the beta matrix. Beta matrix is assumed by the diagonal elements are 2 plus 1 and 2 minus 1. See this matrix, this is beta matrix, plus 1, minus 1, minus 1. All other elements are 0. The order of the matrix is 4 by 4. If you take the sum of the diagonal elements, the sum value equal to 0. That means trace of beta equal to 0. That condition is satisfied. And if you take the square of this beta, beta square is equal to 1. Second condition is also satisfied. If we calculate the eigenvalues of this beta matrix, the eigenvalues are plus 1, minus 1, minus 1. 4 values we can have. 2 plus 1 values and 2 minus 1 values. So all the conditions are satisfied, so that the beta matrix is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. This is reduced as I0, 0, minus I. Say this is I2. This is 0, this is 0, this is minus I2. So I0, 0, minus I. Now we can construct the three other matrices which are anti-commuting with the beta. Now we have to construct alpha x, alpha y and alpha z. Then all the three matrices are subjected for anti-commuting property with the beta. So alpha x is constructed using our sigma x. See this alpha x is 4 by 4 in dimension. 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0 is the value of alpha x. If you concentrate this segment, this is our sigma x. This segment is also sigma x. So that 0, sigma x, 0. In this way, we have constructed the value of alpha x. If you take the trace of alpha x, that is sum of the diagonal elements, the sum value equal to 0. If you calculate alpha x square, the alpha x square value equal to 1. If you take the eigenvalues, if you calculate the eigenvalues of alpha x, we can get 2 plus 1 eigenvalues and 2 minus 1 eigenvalues. At the same time, this alpha x dagger is equal to alpha x, which means that this alpha x is Hermitian also. So all the conditions are satisfied. In the same manner, we can construct the value of alpha y, which is equal to 0, 0, 0 minus I, 0, 0, I 0, 0 minus I, 0, 0, I 0, 0, 0. See the sum of the diagonal elements 0. This segment is sigma y. This segment is sigma y. So this alpha y is reduced as 0, sigma y 0. Similarly, the value of alpha z is constructed using the value of sigma z. Say if you take the sum of the diagonal elements, the sum value equal to 0, which means that the trace of alpha z is 0. This is our sigma z, this is our sigma z. So alpha z equal to 0, sigma z 0. In this way, we have constructed the values of alpha x, alpha y, alpha z and beta. If you want to know the properties of Dirac matrices are Hermitian in nature. They are even in dimension. The dimension of Dirac matrices is 4 by 4. They are anti-commuting in nature. Alpha x beta plus beta alpha x equal to 0. Such a rule we have to apply. Their eigenvalues are plus 1 and minus 1. Their squares are unity. That is alpha x square equal to alpha y square equal to alpha z square equal to beta square is equal to 1. Then if you take the trace values of alpha x, alpha y, alpha z and beta, all the values are equal to 0. Here is a hint I have given to calculate the eigenvalue of sigma y. The same condition is true for sigma x, sigma z and beta also. To calculate the eigenvalue, we have to use this eigenvalue equation. An operator is operating on a function, gives one number lambda and the same function. This is called eigenvalue equation. So ax minus lambda x equal to 0. If you multiply lambda by means of I, that will not affect the nature of lambda. So a minus lambda I into x equal to 0. If you want to take the characteristic equation, determinant of a minus lambda into x equal to 0, here x not equal to 0. Therefore, modulus of a minus lambda I equal to 0. Here, if you want to calculate the value of sigma y, take a equal to 0 minus I 0. Find out the value of a minus lambda I. Determinant of a minus lambda equal to, just take the modulus 0 minus I 0 minus of lambda, then I value 1 0 0 1 is equal to 0. So this is minus lambda minus I minus lambda equal to 0. This is lambda square minus of minus I square is equal to 0. This is lambda square minus 1 equal to 0, lambda square equal to 1. So lambda equal to plus 1 and minus 1. In this way, we have calculated the eigenvalue of sigma y. This is 2 by 2 in nature. If we calculate the eigenvalues of alpha x, alpha y, alpha z and beta, we can have 2 plus 1 eigenvalues and 2 minus 1 eigenvalues. That's all about the Dirac matrices.